Hi, this is the last and final capsule of the entire course, and we call it the road ahead. As the title suggests, we are interested now not in developing further theorems but rather taking a very different approach. So far, we have been looking at vector subspaces of Rn, but now we must look at what are abstract vector spaces, how are they defined, how does linear algebra operate in the abstract setting. So first, let us take a stock of what has been done. We discussed systems of linear equations, elementary row operations, and Gauss elimination, row echelon form. The first chapter was solving linear systems of equations because that is the easiest thing to do. And we're going from known to the unknown. Then what we did was we needed certain basic concepts on linear independence, linear combinations, basis, dimension, rank, first fundamental lemma, row space, column space, etc. Now these were defined in the context of vector subspaces of Rn because that is what we needed throughout this course. Determinants was then discussed in great detail. Determinants of with entries in real, which are real or complex numbers. Sometimes determinants have entries as functions like Wronskian, Jacobians, and so on. And then we discussed inner product spaces again in the context of Rn. And then we came to the diagonalization problem for matrices. When is a matrix similar to a diagonal matrix? We proved the Cayley-Hamilton theorem, and we proved basic properties of eigenvalues and eigenvectors of matrices and the geometric and algebraic multiplicities and stuff like that. Then we went again to inner product spaces. Excuse me. Excuse me. So again, we went to inner product spaces, and we discussed what happens when the matrix is of special character, like a real symmetric matrix or a Hermitian matrix. And then we talked about simultaneous diagonalization of commuting Hermitian matrices, and in fact, unitary diagonalization of commuting Hermitian matrices. And we proved the Schur's theorem, and from Schur's theorem, we deduced Cayley-Hamilton theorem. Now, one could ask several questions. Maybe one can do linear algebra with scalars other than real or complex numbers. Of course, the scalars must form a field: addition, subtraction, multiplication, and division, with the proviso that division by zero is not allowed, and the usual properties of addition and multiplication, like commutativity, associativity, and multiplication distributes over addition, and so on and so forth. In different directions, we could be talking about infinite dimensional spaces and abstract vector spaces. Let us see what generalizes and what doesn't generalize. First, it is important to know that one, the Gauss elimination, row operations, etc., they only depend on the fact that one can perform arithmetic operations of addition, subtraction, multiplication, and division, and it has nothing to do with real numbers or complex numbers per se. One could do it over any field. So one generalizes for arbitrary field. Now let us look at what we've been doing. We've been looking at vector subspaces of Rn. What are the requirements? V1 and V2 are in V means V1 plus V2 should be in V, and V is in V and alpha is a scalar means alpha V must be in V. You may realize that these things hold for many other sets V, not necessarily subsets of Rn. For example, we want to add two things and you want to multiply something by a real number. Now, the thing doesn't have to be a subset of Rn. The thing doesn't have to be a vector in Rn. For example, you could take V to be the set of all polynomials with real coefficients. And I can add two polynomials and the result is a polynomial. I can multiply a polynomial by a real number and again the result is a polynomial. Suppose I take a continuous set of all continuous functions from R to R. If f and g are continuous, the sum f plus g is also continuous. If f is continuous and alpha is a scalar, then alpha f is also continuous. Why are we not considering products? For example, if V1 and V2 are in V, then we could try to define a product. We could try to define a product of V1, V2. The product is some sort. What is the product? You want the product to land up in V. In other words, you want a mapping from V cross V to V with inputs V1, V2 and output in V. Now, but remember, the product here is very different. The inner product is a mapping from V cross V to R. The target space is the real numbers, not V. So why are we not looking at taking two inputs V1 and V2 in V and and output to be in V. Why are we excluding this kind of a thing? The reason, there are several reasons for not including products of this kind with outputs in V. For example, we can consider the set of all solutions of the differential equation y double prime plus 4y equal to 0. Clearly, if y1 and y2 are solutions, then y1 plus y2 is also a solution. If y is a solution and c is a scalar, cy is also a solution. You can directly check this. Superpositions of two solutions is a solution. But if I take y1 and y2 are two solutions, the product y1 y2 is not a solution of y double prime plus 4y equal to 0. So if you demand that if you demand products, if you want to define some kind of a product, and if you want to include these kinds of things, then the scope of the theory gets quite limited. You will not be able to deal with these kinds of situations where of solutions of differential equations. So the vector space, in the definition of a vector space, you confine yourself to addition of two things and multiplication by scalars. That is, V is a vector and alpha is a scalar. V is an entity in capital V, and alpha is a real number or a complex number. Then, and you want to compute alpha V, and that should land up in V. We do not take V1 and V2 in V and try to define a product V1 V2 in V, because the natural things don't really fit into the. For example, solutions of this equation, differential equation y double prime plus 4y equal to 0, will not satisfy that the property that it is closed under multiplication. Product of two functions, if product of two solutions is not a solution of the differential equation. So we want to keep the theory quite versatile, and so we don't want to put in too many things as definitions. So we want only the addition, v1 plus v2 should be in V, and multiplication by real numbers should again give you back a vector. Okay. So now in MA207, you will study this differential equation: 1 minus x squared y double prime minus 2x y prime plus p into p plus 1y equal to 0. Students of physics may recognize this as the Legendre equation. Now, p is a constant. The set of all solutions of this differential equations is a vector space. If y1 and y2 are two solutions, y1 plus y2 is also a solution. If y is a solution and alpha is a scalar, alpha y is also a solution. So the solutions of this differential equation forms a vector space. You will see in MA108 that this vector space has dimension 2. So notion of basis, dimension, etc. can be developed for abstract vector spaces. In an abstract setting, you can discuss the entire chapter 2. The whole of chapter 2 can be described. Linear dependence, linear combinations, matrices are don't think other than matrices. Anything to do with linear combinations, linear independence, basis, dimension, and the first fundamental lemma. All of these concepts make sense for abstract vector spaces. And in that context, the solutions of this differential equations forms a vector space of dimension 2. And that you will see why that is so. You will see why that is so in MA108. If you're curious, you can look at my handwritten notes in my website. So, how do you describe linear independence, linear dependence? If y1, y2, yk are functions, or if V is a general vector space, for example, vector space of functions, for instance, and you say y1, y2, yk are elements of V, you say that they're linearly independent if whenever a linear combination becomes 0, all the coefficients must be compulsorily 0. Here, equality has to be understood in the sense of functions. That is c1 y1x plus delta plus ckykx is 0 for all x in R, for all elements in the domain. So for example, sin x and cos x are linearly independent, because if you stipulate c1 sin x plus c2 cos x is 0 for all x, then in particular it must be true for x equal to 0. That will force c2 to be 0. It must hold for x equal to pi by 2. That will give you c1 equal to 0. So sin x and cos x are linearly independent. Given a vector space V, an inner product, again we can define an inner product in a very abstract setting. V could be a subspace of Rn, V could be the solutions of a differential equation, or V could be a set of all continuous functions from R to R. Various things you can try, and you can try and define an inner product. Given two elements phi1 and phi2 in V, the inner product, triangular bracket phi1 phi2, is a rule, is a mapping, triangular bracket is a mapping from B cross V to R such that the usual properties are satisfied. By linearity, it is linear in each variable separately. Symmetry, and then symmetry and positive definiteness. That's a triangular bracket phi is non-negative, and it is zero if and only if phi is zero. Of course, if the vector space is a complex vector space, then phi1, phi2 triangular bracket will be phi2, phi1 bar. The bar has to be put in, and lambda of phi1, phi2 will be, lambda will come out if the lambda is the first variable. Phi1, comma lambda phi2 will be lambda bar of phi1, phi2. So these are the usual modifications for a complex vector space. But all concepts of chapter 4 carry over in this abstract setting. Orthogonality, orthonormality, unit vectors exactly go through. A set of non-zero vectors which are mutually orthogonal are linearly independent. The same proof goes through. Pythagoras' theorem goes through. The parallelogram law goes through. Cauchy-Schwarz inequality goes through. And the proof goes through without any changes. Gram-Schmidt's process goes through without any changes. Of course, if the field is a complex field, then it's going to be a Hermitian product, not an inner product. So what happens when we try this out with a general field other than real numbers or complex numbers? When you talk about inner products, we are very careful to work with the real numbers or complex numbers. The reason is very simple. The trouble comes from this requirement of positive definiteness. What is the analog of positivity in an abstract field? That's a very complicated problem. So that's why in most cases, that's why we don't venture too far away from real or complex numbers. So chapter 4 and chapter 6, those which are special for the real and complex scalar matrices, many of those concepts carry over for general vector spaces. Schur's theorem demands unitary triangulability. That is, given any complex matrix, there's a unitary matrix U such that U star AU is upper triangular. The fact that this matrix U is unitary, that is extremely important in many applications. I mean, if you drop unitary, then if you don't work with complex numbers, then we can't expect, then you have to drop unitary also, because orthogonality inner products are not defined for general fields. So instead of U star AU, you'll have P inverse AP. So the theorem is that if you have a matrix of complex, if you have a square matrix whose entries are in a field other than the complex field, then the appropriate problem to think about is that whether it is similar to a triangular matrix. Here we are asking that it is unitarily similar. Unitarily similar is very strong. Here we ask for mere similarity to a triangular matrix. The answer is yes, provided the characteristic polynomial factors and has its roots in the field. So one can again use this weaker version to prove the Cayley-Hamilton theorem. The proof goes through word for word. So chapter 5 on diagonalizability will go through without any changes. You have to be very careful. There's only one small warning. There are fields which are called fields of finite characteristic. The characteristic of a field could be, say, 5. It's a prime number always. And then if that is the case, then division by that particular prime number is forbidden. So there are certain restrictions in the arithmetic when you work with certain fields. Clearly, these things are outside the scope of MA106, and I don't want to dwell on these subtleties. I just given a word of warning. You will know when you encounter those kinds of fields. You will know what to do and what not to do. So let us look at inner products in vector spaces of functions as a sample, for instance. So for example, I can take the set of all continuous functions on the closed interval -1, 1. I can define an inner product. Inner product of f and g is integral from -1 to 1 fx gx dx. It's an exercise for you to show that all the properties are satisfied. If I take f1 plus f2 and then comma g and inner product, it will be integral f1 plus f2 into g. So integral is additive. So integral f1x gx dx plus integral f2x gx dx. And so that will be triangular bracket f1g plus triangular bracket f2g, etc. Symmetry is obvious. So all the proper positive definites you have to check. please check positive definiteness. So, for example, if I describe orthogonality in this way, check that x and 1 minus x squared are orthogonal with respect to this inner product. Let capital D be d dx, the derivative. And let us take this polynomial x squared minus 1 to the power n. X squared minus 1 to the power n is a polynomial of degree 2n, and I differentiate it n times, I get a polynomial of degree n. This polynomial is going to be denoted by Pn tilde. Why Pn tilde? Why not Pn? Because I need to normalize it in suitable way. When Pn tilde is normalized suitably, you get Pn. So now I want you to check that if m and n are not equal, then this Pn tilde and Pm tilde are orthogonal. Hint, integrate by parts. This kind of situation is going to arise in quantum mechanics, in many other parts of mathematical physics. It's going to appear in numerical analysis in the theory of Gaussian quadratures. And you will study this in MA207. Again, my notes are available on the website. If your curiosity has been aroused, you can check my notes. So, third exercise, is it true that cos 2 pi x and cos 3 pi x are orthogonal with respect to this inner product? Suppose I go from minus 1 to integrate from minus 1 to 1, cos 2 pi x into cos 3 pi x dx. Please check whether you get 0 or not. So, are they orthogonal? How would you prove that e to the power x, e to the power 2x, e to the power kx are linearly independent vectors? As function, if you think of the set of all functions from R to R, how do you prove that they are linearly independent? So this is the kind of questions that you can think about when you want to go for abstract vector spaces. Again, I think I'd like to close this capsule here with a few words. We started out very modestly. We're talking about systems of linear equations and Gauss elimination. We started from very, very familiar territory, and I think we have covered a substantial bit of material in about 14 hours of lecturing. And I think this coverage, I think with this background, we have got a very, very strong background in linear algebra in Rn. We are not talked about linear transformations and many other things, which except in passing in examples. We looked at a few examples like shearing transformations and other things. Other than that, linear transformations have not made their appearance. I think that now your transition to a more general study of to more general vector spaces is going to be easy. I think you're ready now to embark upon a more systematic and a more advanced parts of linear algebra. Linear algebra is going to be used everywhere. It's extremely important in calculus. It's extremely important in control theory, cryptography, coding theory. All parts of mathematics will use linear algebra. And I hope you enjoyed this course. I'll stop here. Thank you.